otherwise you could squeeze them in, and you could go to both the Tuesday and the Thursday lab sections as well to try to make up. I don't know how many labs you need to make up.
Two. It's two.
Yeah.
I'll try and I have I'll come in on Mondays and Wednesdays. There's a test next week, isn't there?
Yeah.
What day?
It's on Thursday.
Um,
So yeah, hopefully you're ready to take it. If not, we could try to make alternate arrangements.
I've been looking at tutoring at the tutoring center to help me, make up some of the time that I've lost. But I'll keep it updated because chemistry isn't easy for me. But I'm trying to do my best to keep
And then I can always meet with you as well. You just have to make a time. And... Other questions or?
That's it.
Okay.
The lab for the periodic table, I did my best. The one I had to do at home, that one, I just wanted to share. Like it was.
Or the
hard.
card one?
Yeah,
Oh.
the layout was hard alone. So yeah, I'm turning in is kind of sad, but I did my best.
We could talk about it later too.
Can
if
we?
have
Okay.
questions. Yeah. All right, let's go ahead and get started, but let's kind of warm up with this question. So I've had it up here, but we'll let people look at it. And so if you're in the chat, say hello, and then you can type your answers in. So examine these quantum numbers, determine whether they're allowed or not, and then offer some sort of correction. How could we fix it to be allowed? And so there could be different ways to correct it. And then I'll try to hand out more papers. So I'm still a little behind from the first crop. So if your grade is still missing and you turned it in a while ago, don't panic quite yet. I'll hopefully get through the stack this weekend, and then by Monday, your grade should be more accurate, is the goal. Yeah, so I'm going to try to hand back papers. probably take another last minute or so, and then we'll go over them. So again, if you're in the chat, you can put out your answers. So let's hear some thoughts. So what do we think about this first one? So n equals 2, L equals 1, M sub L is 0, and then spin of 1/2. How does this look?
I think that's correct.
So I see a lot of thumbs up. And then what type of orbital is this describing? How could we write it?
2p.
So 2p. Everybody feel good about this? So 2p, and then of course just identifying one of those 3 p's. Excellent.
And so would the electron be in the middle orbital if you like draw out the 3 lines and then?
So that whole thing of like which orbital is it really in, like we could say it's in the middle one, but we don't really know, right? Because it's not a standard that's been standardized. We're just kind of saying it's in one of the 3. Does that make sense? Like it's just there's no set correlation. So you could say that, right?
In that
But
case, I don't know what the ML stands for.
well, it literally just stands for any of those 3, right? But all I'm saying is like don't get attached to the 0 being the middle one, right? That's all I'm saying. Is it just you're just identifying where it could be, potential sets, right? But we're not truly identifying a specific orbital.
Okay.
So it's kind of, yeah. And you can, in your brain, you can kind of say, yeah, it's the middle one, you know, in this thing. But I'm just saying, like, there's no standard of translation for that. And, like, it doesn't correspond to, like we won't say that this is PX, right? That's not a universal standard. You can just assign it arbitrarily.
Okay.
So what about this? Oh, so that's just a spin. Oh, thank you so much, B. Quiz is behind. So the MS is just a spin state. And so that represents, so how I always draw those little electrons with the half up or half down. And so as long as it's either plus 1/2 or negative 1/2, either one of those are appropriate. And we didn't restrict it, so we didn't say like, oh, there's already an electron occupying this value. So any of those spins were okay. Yeah, so you can't have 0, you can't have 1, so you can't have any integers. It's either plus 1/2 or negative 1/2. Correct, yeah, so any appropriate allowed value, yeah. And so we could write on there, right, 1 would have been okay, negative 1, doesn't matter. Yeah, like we established, we're not truly assigning it to any specific one, we're just saying it's one of those 3. Excellent. What does this one look like? So we have,
It looks incorrect.
so what's wrong with it? Why is it incorrect? So, or what'd you say? ML? M sub L?
Regular L?
Yeah, L has to be n minus 1. That's correct, but that's fine, right? So it can take any values of 0 to n minus 1. So it can be, so this is, we can still write this, so this is fine. But it starts at 0 all the way to n minus 1. And then M sub L, while we're on this topic, right, we said that then that takes values of negative L to positive L of integers. And so what's wrong with this?
It's saying that it has an extra, like, orbital that it doesn't have.
Yeah, so we have either unallowed values of M sub L, either mathematically, we could only have 0. If it's a 0 for our L, what kind of orbital is this again?
That would be 3s, right?
Yeah, so 3s, but then, so this is incorrect. So how could we correct it?
That would have to also
So 0. Or, of course, right, you could change this. Well, if I want to allow this value, let's change it to, an L. So I could put, right, alternative answer. So this would be correct, like on an exam, if we said correct it. So 3, 1. And now if we have 1, then we can allow 1 as our m sub L, so one of the p orbitals. So either way, so I'll correct this. So this is a 3s orbital as it stands with the 0. Or you could have offered a correction to make it a p. And really, right, you could have also done a d orbital, so 3d would be allowed, just while we're at it. So 3, 2. So 1 would still be okay. So that would be fine. Again, you just have to correct that L value. Yeah, so this is fine. So this is 1 offer. So 3, 0, 0, negative 1/2, or changing the L to reflect, the m sub L. Excellent. Good job, you guys. What about this one?
That one looks correct to me.
So I see a lot of valid thumbs up. And so what type of orbital is it describing?
It's 3D.
So 3D. Excellent. So our 2 is our D. And then again, just one of those 5s arbitrarily assigned. How does this next one look here? 1, 1.
I don't like it.
1P.
It's saying that it's a 1P, which I don't think exists.
Excellent. So we could, probably the easiest correction is change that back to a 0. So we're in the 1s. And then if that probably matches. I mean, it doesn't really matter. You could have changed this as well, right? Change it to 2. So I'll put that as an alternative answer. So valid. So if we had done 2, 1, 0, 1/2. And then what about this last one? So 2, 1, 0, 0. How does this look?
It's a 2P, but with no electrons.
Yeah, we can't have 0, so not valid. Who knows what this is saying? And so we could put, and you could put negative 1/2, so it doesn't matter however you're feeling, positive or negative 1/2. And so what did we say this was again? What's the one?
2P.
2p. Excellent. Excuse me. Any questions on this one? We feel okay about quantum numbers?
So would ML, like it's restricted by the L number, so like whatever the L number is, the ML number cannot exceed the absolute value of that number.
Yeah, so then I have that.
Correct?
Yeah, so I rewrote it here. So, right, m sub L is negative L to plus L with all those values. And your test will be open now, I've decided. So
Thank you.
we'll see how long it takes me to grade. Now, power through. All right, let's try these next ones. And so again, you might see this on the exam, so it would probably be like a multiple choice question for that one, and it would just say like, either choose the one that's allowed or choose the one that's unallowed, so something like this. But y'all seem like you got the handle on this. So now practice writing your electron configuration, and so using the arrow notation. So that just means setting up with the orbitals. You can also write it in kind of the box notation if you prefer writing it in like boxes next to each other. So give that a try, and then we'll probably send people to the board to look at your variations. All right, let's do nitrogen. Let's start with that one. So who wants to put nitrogen on the board for us? All right, go for it, Vaughn. I saw your hand up. I have another marker. Here, I was going to toss it. Oops, okay. I'll try to hand out more quizzes and everything. I feel like you drew just one too many boxes in the P. But other than that,
This, do you only draw the boxes that you need? You don't draw all the boxes in the
yeah, so like the S should only have one box as well, so I would just erase the line.
Oh, I see, okay.
Yeah, because each box represents an orbital.
Right.
So that looks, wait,
Yeah.
keep your lines on the P. Yeah, there we go. So that looks good, so I'll rewrite it. And of course, right, so again, you can write it the boxy notation, like he drew on the board here. So 1s, I was copying that. And right, each box represents a different orbital. And so good with filling the one electron in each degenerate, yeah. So I would at least include the 2s and the 2p, but yeah, you don't have to include the core one. And so I'll write it, again, alternative. So at least do the valence ones. And again, I'll just fill it up. All right, who wants to put magnesium on the board then? Yeah.
So when you're writing it, like, just with the lines like we did on the right, well, my right, do you have to do it like leveled like that, or can it be like straight out? So you do 1s and then 2p.
You're talking about
2s,
like that?
yeah.
This would be okay as well, just as long as you realize later in your mind that you're doing like the 2s fills up first and then the 2p. Yeah. I just like writing it like that because of habit too. And like later, once we do MO diagrams, like the P is higher than the S, and we'll get into like mixing. But yeah, is for just this purpose, this is also okay because that's the same as like the box notation. Any other variations, permutations? All right, somebody throw magnesium on the board. That one shouldn't be too bad. I think Phoenix is on his way, but do you want to do sulfur once he's done? Okay, we'll put you down for sulfur. I'll try to get. So it looks like we went for the gold here, showing everything. So you could have just shown the 3S, that would be okay. I like how you did everything, so showing the 1 and 2P, that looks excellent. I have no complaints about that. So let me copy that down. So that looks good. And then Madeline, if you wouldn't mind, we'll get you on deck. Worst case, I think you could flip the board, like physically flip it, or rotate it rather. Only has rotational freedom.
This is what I got. I just did the valence electrons.
Wait, I think you have too many p orbitals or something. There's something funky going on. How many p's are there? Yeah. So 3p, and then we probably want to show the 3s just for completion. So then 1, 2, 3, and then we pair. And I just showed the 3s as well so we can tell, right, that it has 6 valence electrons. We could have, yeah. So that looks good there. Which one do we have next? And then who wants to do neon for us? Alero, you made eye contact? No.
Leo, you have to now.
All right. No pressure. All the pressure.
Well, you did all of them.
So did you do 2 variations? So I'll copy the one how I usually write it. And so I'll just do the lower energy. But yeah, that looks excellent. So all of them are filled. They're all paired. 3p orbitals. And yeah, you drew out everything. So also going for the gold there. And then, of course, you could write it in the box notation. Any questions about those? Yeah. No, you could have also just shown the valence. And probably on the exam will like specify to show like the valence electrons since that's usually what we care about. All right, so now try this one. And let's see, we're kind of running out of time, or at least I want to hit some other stuff. So let's just look at bismuth and platinum. So look at these two. And then we can go back and practice. I just want to make sure we hit some other examples. And if you're in the chat, again, you can type your answer out. So does someone want to put bismuth on the board for us? Go for it. I don't see any victims. Then you can probably erase. You want to do platinum?
Yeah.
Okay. We'll put you on the volunteer list.
If you have no other victims for platinum.
Cool. So make sure you didn't skip anything. So
Don't forget the 5D and the 4F.
Right. This is what I do for getting hubris and not looking at my notes beforehand.
So I think we've identified we're missing something. And so this is a good point to remind yourself to double check. So let's not look at this one. I guess we can look at this one. So right, we started with xenon, so you're at 54. But then if we go back to our answer, so 54 plus 5, so we're definitely missing some stuff. So we're at 59. So then what are we missing? I'll pull up the periodic table too. So you're at xenon.
Yeah.
Which I think it's 4F 14?
Yep. So following in pattern, 6S of 2. Yeah, so 4F14, and then don't forget, so make sure you write that in.
I like the way you write your Fs. It's very pretty.
5D.
Yeah, and that should be filled, so 5D10.
And then 6P, whatever. Yes.
So now that looks complete, and then again, double check yourself. So we were at 59, and then, oh yeah, we forgot. So 14 plus 10, and so, okay, now we're at 83, so that works for the neutral, yeah. I won't be too picky, and so, right, probably ideally you want to try to write it in order, but I won't dock you for that. Yeah.
When we write out the actual orbitals for 6p, all of those electrons are unpaired, right? In the
Correct.
6p3.
Yeah, so the 6p3, so let's just write that then. Correct, so that would fill up, there's only 3. Yeah, and that also makes sense because if we look at our periodic table, well, bismuth is under nitrogen, so just like nitrogen has those 3 unpaired electrons, yeah, it follows with that pattern again. So that, now you're at least asking the right questions, so that's how we're gonna figure out, right, that next step, so we know, well, this one has 3 unpaired. So let's throw platinum on there, and then we'll look at this more formally. Right.
2, 4F, I'm using F14,
Yeah.
5D10,
So then, yeah, 5D. And so we could double check ourselves. So platinum, so we're at 54 plus 2 plus 10 plus 8. Wait, did I do that wrong?
14.
Oh,
That's right, the S is 14.
why did I write 10 on here? I don't know why.
Probably because I said 40, 10.
I don't know what I was. Sorry, let me add that again. So 54 plus 2 plus 14 plus 8. So 78, so that matches. And so this is what we expect. And then, so the only issue with this one is so it behaves a little oddly. And so I'll just say, right, this is a correct answer. Again, what we expect. But just know that if you were to check it on the P table, it is one of those odd ones. Oops, that's not what it does. So one of the electrons from the S, it only has one in the S, and for some reason has 9D. So, yeah.
Is there a simple explanation to why that is?
Oh, well,
Yeah,
that would
because
be,
it doesn't fill up its d orbital
yeah.
all the way.
Well,
So why?
I mean, we could try to guess as to why. It's also kind of how it behaves. So platinum does do, you know, your one electron, so it does do like platinum 1 plus. But actually, platinum is really cool because it's more powerful than like nickel, so it can do like multi-electron transfer. But it also depends like what geometry it's in. But yeah, you could try to do the analysis because, right, so 5D, so 1, 2, 3, 4, 5. Oops. And so what we expect, so we could compare. So 8 in the D, so 1, 2, 3, 4, 5, 6, 7, 8. And so then we expect it to have 2 unpaired versus the reality. So I'm not filling it up properly. So 9, 6S. So that's a little interesting.
Why wouldn't it just take everything out of S to put them in D and then have a full D orbital? Is that even possible to have?
I mean,
S with zeros?
well, that's probably what it's going to, well, it's going to lose, right, an electron probably from the S when it reacts. But it is a little odd like that. And then it probably just has something to do with the geometry more of the d orbitals. So this is like a limited explanation. And so that's kind of the problem with this is that we don't really get a full picture. So we'd have to go into like crystal field theory because that's probably why there's some weird shifting. And so probably why it feels this way is like the 6s is a little higher because probably some of these d orbitals go down in energy with the geometry. So that would be my explanation, but it's
So
just,
remind me, the 6s orbital is like physically farther away from the nucleus, right? Or is it physically closer than the d orbital?
well, that's a tough call, right? So that's kind of where all these oddities come in, right? So they're pretty close in energy. So if you can look, the 6s and the 5d, that's really close. And then when we're talking about it, this is mainly, it's just like it's ground state elemental. But then when we're talking about like what it really does, it's going to go into a different geometry, and the different geometry will throw those d orbitals into different energy levels. So this isn't really how they behave, right? So this is still an oversimplified picture. And so what's probably happening is something when the 5Ds split, and again, so it could be something like that. So the 5Ds are funky, and then maybe the 6S is somewhat higher so that it fills in like is actually noted versus what we predict from our just simpler filling in. And that's, yeah, so we'd have to, again, get more like data then, how does it behave? And then some of that is figuring out right pairings and where those electrons are coming from. But That's our best guess. Anyways, as long as you have kind of what we expect, that's fine, right? That's the level we're at this course. So let's do some of these practices. So now, try it for all of them, although we'll probably do germanium and selenium first, and then we'll take a little thought break and then look at vanadium and iron. So definitely try germanium, selenium. I'm watching the chat too, so you can put your answer. So let's put germanium on the board. So who wants to do germanium? So I'd probably still write our little arrow notation to kind of help us. Yeah,
I think I know what it is.
let's try it out then.
I started with argon. I went down to 4s2, 3d10, and then 4p2. So we have 1, 2, 3. Like that. So these would be invincible electrons. We would have 2 unpaired valence electrons.
Excellent. So answer 2 unpaired. And so how you drew it was nice. So we could just focus on the P and the S, so 4P. So there's just 2 in the 4P. And so, right, the unpaired meaning they're not paired in their
They
orbitals.
don't have an upwards and a downwards arrow?
Yeah.
Okay.
And so unpaired. And so when we have this with unpaired, this is actually a special term as well. So this is called a paramagnetic. So something that is paired, which now I don't have a thought in my brain. But if we were fully paired like neon, Get back to neon just for a quick minute. Neon's in the soupy though, my bad. And so right, neon, so this would be considered diamagnetic since it's all paired. And so some significance of this and how you could tell is, so if you had a diamagnetic compound, and so that usually means it's like a normal behaving compound, so usually like an organic compound. If it behaves nicely, it'll go in your NMR, give you nice sharp peaks since they're all paired. But the funny thing about paramagnetic compounds then in the NMR is since they're unpaired, then they have a much longer relaxation time. So they would give you a spectra that's all blobby, essentially. And so this can happen in the presence of certain metals. So if you add like a metal to your nice organic compound and it gets all blobby looking, but it looks not like poop, which like really is a good indicator of your reaction. Like if it looks like shit, it probably is shit. Like, right? You can have that quote. But if it looks like a good color, right, blue, purple, green, something promising, and it looks paramagnetic, then that's probably giving you some indication of what's going on with that metal, that indeed it is paramagnetic.
So paramagnetic things in the spectrum appear as like weird, funky colors?
Yeah, not funky colors. It's with the NMR. So basically, well, we have to show what an NMR is. So let's just look at like a benzene NMR really quickly. So like a NMR normally looks like really sharp and defined, and then if you go to OChem, you'll learn how to read this. So it looks nice. I don't know if I can find paramagnetic. So just trying to get a sense of what it does. Sorry, I was trying to find a good picture. Let's find a better image.
Oh, so it's not colors, it's just like lines on a.
Yeah, so it's like lines. So it starts getting broad basically, and it looks weird, right? So like this is kind of a comparison. So it should look sharp, but then if it's paramagnetic, it starts getting blobby, and like
the mountain base.
Yeah.
Wider.
Yeah.
Instead of like this.
And then sometimes the shifts would also expand to like a wider range, but now we're kind of like going too far out of the course. But that's just kind of an idea of what happens is like now because it's unpaired, it's a lot broader relaxation, it's not as sharp. And so when you do the NMR, it gives you this weird signal. But that's where I was saying is kind of when you're doing research, you know, you're like looking at the blobby NMR, you don't want to be like, oh, it's trash. You know, just because you can't tell, it's like maybe it's paramagnetic. And that's also how you know it's paramagnetic, because things start changing with your spectra. Yeah, but the colors just have to do with, right, the transitions that we're talking about, kind of like those allowed transitions with our electrons. It's just that the transition metals, those are all allowed since they're in like the d orbitals, so those are in the visible region. But organic compounds, right, that's why they're white, because it's all in the UV region. All right. So let's throw up selenium. So does anyone want to put selenium on the board? Right, go for it, Vaughn. And then start thinking about vanadium. We're kind of running out of class time. Or at least.
For these type of questions, do you want them written out, like with the full electron configuration, or
Yeah.
Like for this one, it's 3. Like,
It's probably better to show your work, and like probably I would do like a multi-layered question of, like write the electron configuration, how many unpaired, and I always say like I'm generous with extra credit. So like the only thing is, so if you just put like 3 unpaired, and let's say it's wrong, right? I can't go back and like try to logic through what you were thinking. So there's like a slight risk there, but.
Yes, that's what I got as well. There's 1 paired set and then 2 unpaired electrons.
So it should look something like that. So that looks good for the electron configuration. And then I just wanted to show the 4p, or you could have just written however many, so 2 in this case. And then let's do, so what do we get for vanadium then? So I heard a 3, so in the interest of time, so 3 unpaired, and I'll throw it on there. So then we had 3D, so for our electron configuration, sorry, starting at argon, oh my gosh, all over the place. 4s2, 3d, 3. So then our 4s was filled. 1, 2, 3, 4, 5, so 3 in the D there. All right, I'll just kind of show you other representations. So we can continue on Tuesday with kind of more practice. I don't want to take more time since we have the quiz to do, but at least get a taste of what else we're going to talk about. So identifying whether this is neutral or excited. And of course, right then you can just count the total number of electrons since it's neutral, or right, if it's charged, obviously you can compensate, but then you could tell, so this one is 2 plus 2 is 4, plus 6, so 10, so that's an excited state of neon. But I'll leave this up here so you can think about it. I'll probably stop here so we can take our 10-minute break. If anybody needs to leave, I have the quizzes. Otherwise, I'll pass them out in 10 minutes. And then, of course, I'll answer questions. And if you have questions, right, use your recitation time to ask questions and get anything completed that you're missing. All right, I will hang out on stream for another minute or so, and then just email me if you have any other questions.